Little's law. So Little's law is a very useful formula that is useful to know to do some back of the envelope calculations involving how many people are or units are in the process, how much time they spend in the process, and so on. So some basic statistics we can calculate using this theorem. So the formula is very simple. I like to write it like this using L, lambda, and W because it just reads like law. L, lambda kind of looks like A, and then W. So it's very easy to remember. You'll never forget it. Okay, law is the formula. Just put equals after the L, and the lambda is the A in the word law. Okay, so L is the number of units in the system. So this is, if you're looking at a process, is all the units in the process. They could be being worked on at a certain stage. They could be work in process inventory between stages, but everything in the process, the number of units in the process or number of customers in the process is L. Lambda is the average arrival rate. So over a period of time, on average, what is the arrival rate of units entering the system? So let's say for a service process in healthcare, it could be the number of patients that arrive for that to be processed by that process. And W is the throughput time, the average time a unit spent in the system. Now, this Little's law recognizes that arrivals and the time spent could be variable. So the average arrival rate could be 5 patients per hour, but some hours we may get more than 5, some hours we may get less than 5. That's fine. We work with averages. So this formula applies to long run averages. It only gives you the average statistics or parameters for the process. Again, W is the average throughput time. So some patients may get done quicker, some patients may take longer because in some processes, the cycle time is not fixed, right? So on average, it takes 5 minutes per unit, but some units take longer, some units take less. A classic example is the checkout in a grocery store. Not all customers' checkout takes the same amount of time. I'm sure you've been stuck behind somebody whose cart is overflowing with stuff and it takes like 15 minutes to check them out. And then you're stuck in line for a long time. And maybe you've also experienced being behind somebody and all they got is a pack of soda bottles or something because maybe they're missing drinks and they just check out in 30 seconds or a minute, right? So the cycle time or the processing time can vary. The waiting time can vary depending on how crowded the system is, how many people are in the system. So because of that, the throughput time can vary, but we're talking about the average here, the average throughput time. So if you know 2 of these 3 things, if you know L and lambda, you can calculate W. If you know lambda and W, you can calculate L. So if you know any 2 of them, you can calculate the third. Now there are some assumptions about this theorem that have to be true for it to work. The first one is very important, which I've already hinted at. It is the theorem works on long run averages only. Okay, at a particular snapshot in time, L may not equal lambda times W if L is the number of people in the system at that particular time, and lambda is the arrival rate at that particular time, and W is the throughput time at that particular time. Because as I mentioned, these things can change, but we're talking about the average. So the law or the theorem only holds on average. What this means is if you have a process or a system where there are busy hours or peak hours and non-busy hours or non-peak hours, then what this theorem gives you is going to be the average. So the peak hours may be different. You may have more people than what L you calculated. And then the non-busy hours, you may have less people than what L calculated by this theorem. But on average, or the L gives you the average. So you have to be careful if you have busy times of the day and so on. When we do the examples, we'll think about how to interpret the values we calculate, and I'll talk about it a little bit more there. The second assumption is it's a stable system, which means the arrival rate lambda is roughly equal to the exit rate. Okay, this happens when the bottleneck is not holding up your system. So the arrival rate is less than the bottleneck, because you do not really have a stable system if the arrival rate is more than the bottleneck capacity. Let's say you have a process with a bottleneck capacity of 12 units per hour. So your process capacity will be 12 units per hour. If the arrivals are higher, like 15 units per hour, then the output of the process, the people or units leaving the process, will still be capped at 12 units per hour because that's your bottleneck capacity. But because the arrivals are more, they're 15 units per hour, your WIP will start to grow and grow and blow up, and eventually your system will not have space to store all that stuff. So that's not a stable system. But if your bottleneck capacity is 12 units per hour and the arrival rate is 8 units per hour, now you have a stable system, because the arrival rate is going to roughly equal, on average in the long run, the exit rate. So if 8 people are arriving per hour, on average 8 people are leaving per hour. So you have a stable system. Things are not blowing up, queues are not blowing up, WIP is not blowing up. And so for this theorem to hold, that also has to be true. If your work in process inventories keeps growing and growing and growing, I mean, it will go up and down because arrivals could be random, but if it just keeps growing systematically or it keeps shrinking systematically, you may not have a stable system. That may mean that, you know, your arrival rate is changing, is either higher than the bottleneck capacity, and so your system can't keep up, or things like that, right? On average, the theorem holds, and the system has to be in a stable state. Let's look at an example. So let's say we want to staff a call center. We know that we get 90 calls per hour, and the average call to our call center is 10 minutes long. Because our arrival rate is in calls per hour, we have to convert the 10 minutes to hours. So we divide 10 by 60 and we get 0.167 hours. So how many calls are in the system on average? This could be useful for us to determine how many phone lines we need, how many people we need to handle the calls, right? So we do L equals lambda W. Arrival rate of 90 is lambda, and the throughput time is the duration of the call, which is W, right? And obviously throughput time also includes waiting time. So if the calls have to wait, then you have to add 10 plus the waiting time. But here we're assuming if we don't want the calls to wait, if you want to have sufficient capacity that a call comes in and it's just taken right away, then what does L look like? So if we assume the throughput time is going to be the call duration, that there's basically no waiting time, then we can plug in 10 minutes or 0.167 hours for W, and then we get L equals 90, the arrival rate, times W, 0.167 hours, equal 15 calls. So if we don't have waiting in the system, we'll have 15 calls on average in the system. And so you may want to have staff to be able to handle 15 calls at the same time. If you have less staff, you will have waiting, and then your throughput time will go above 10 minutes. Also, even if you have 15 people to handle 15 calls at a time, sometimes there might be some waiting, because as we mentioned, this is average. So on average, there are 15 calls in the system. There'll be times when there'll be less than 15 calls in the system if the arrivals are random, and there'll be times when there'll be more than 15 calls in the system. Yeah, but it's useful to know, right? It's useful to know how many calls are there on average. So at least on average, if you don't want there to be any waiting time, you can staff the call center properly. A hospital emergency, I forgot to mention that when the arrival rate is roughly, it doesn't mean exactly, but over the long run, the averages are about the same. If the arrival rate is roughly equal to the exit rate, then we can rewrite the formula in a little bit different terminology that some people like to use. Okay, instead of L, which is like length, which refers to how many things are in the system, they like to use work in process WIP, because anything in the system, they consider that as work in process inventory, right? And then the arrival rate, because it's approximately equal to the exit rate, we can plug in the exit rate. Exit rate is also called the throughput rate. That's the output rate, the rate at which a process outputs things. So we can replace lambda by the throughput rate or the exit rate of the system, and we can multiply it by the time spent in the system, which is also called flow time in this alternative specification. So it's exactly the same thing. WIP is your L, throughput rate equals lambda in steady state on average, and flow time is by definition the same as throughput time, the same as W. Okay, this WIP equals throughput rate times flow time is often a preferred terminology by people who like to think of, in operations, who like to think of throughput time as flow time, and throughput rate as the output rate. So just alternative terms for the same things, and so you can rewrite the formula as this. You might see when you look up Little's law in textbooks or other places, you might come across WIP equals throughput rate times flow time. You might say, well, I learned Little's law as L equals lambda W. Well, it's exactly the same thing. Okay, they're just calling L as WIP, they're calling W as flow time, and throughput rate is slightly a different thing. It's the exit rate, where lambda is the arrival rate, but in steady state, in a long run average situation, they should both be equal for a stable system. So lambda equals the throughput rate, so you could plug that in. Okay, let's look at the second example where I'm going to use the second version of the formula just so that you're familiar with it. So a hospital emergency department gets 60 patients per day, and the average flow time, or the throughput time, the time person spends in the department, is 8 hours. Again, because the arrival rate is in patients per day, we need to convert this time into the same units of time. So we have to convert 8 hours into a day. And so 8 over 24 hours is 0.33 days. What is the work in process on average? So how many people are there in the emergency department on average? Because that may help us determine the size of the emergency department, how many beds you need in it, things like that. So the WIP will be equal to throughput rate, which is 60 patients per day, times the flow time, which is 8 hours, but we have to put it in days, not hours. So that's 0.33 days. And when you multiply them, you get 20 patients. So on average, there are 20 patients in the emergency department. Okay. Another way this theorem is used is to figure out the throughput time, because that's the time a customer spends in the system. So when you design service operations like bank branches, healthcare facilities, and especially things like bank branches where people can switch to a different bank if they're not happy, customer experience takes on higher importance, and the throughput time is very central to customer experience, because if the customer spends too long doing something simple, they're not going to be happy, right? So let's say there's a bank branch which has 10 customers inside on average. So maybe you're the manager of the bank branch. You count how many people are in the bank branch at different times of the day over, let's say, 7 days or a month, and you calculate the average. So on average there are 10 people inside your branch at any given time, and 20 customers arrive or leave per hour. On steady state, this should be the same, the arrival rate and the exit rate. So about 20 customers are either arriving per hour or leaving per hour. So what is the throughput time or flow time? How much time is on average a customer spending in the bank branch? Okay, so we've said L equals lambda W. L is 10, the number of people in the system at a given, on average, at a given point in time, or at a point in time. That equals 20, which is the arrival rate or the exit rate. They should, on average, they're about the same, times W, the time spent in the system. So W becomes 10 over 20 in 0.5 hours. We know this is hours because this was 20 per hour. Okay. And so the units of this lambda are going to tell you the units of W. Okay, so W is equal to 0.5 hours. So then you might think, oh, is that good or bad? Maybe customers are not happy spending half an hour in the bank branch, so maybe you need to increase the tellers and so on and so forth. Now, more complex analysis of this sort of these sorts of situations can be done using simulations or queuing theory formulas. But this is a simple first cut high level analysis that is also very useful. And then, we can learn more about other more detailed analysis as well. Okay, now we're going to solve some examples just to reinforce all the ideas from process analysis that we've studied. I'm going to go through these examples a little bit quickly because I know you can rewatch the video if you don't understand something. Hopefully, given that you've spent so much time discussing these things, what we do here is going to be clear. and not a surprise. So we have this process at a bank. And this is the loan applications process, the process we use to reject or approve loan applications. So we're asked some questions about the process. Which step is the bottleneck? Then what is the capacity of the entire process, which will be the capacity of the bottleneck step? What is the throughput time? What is the maximum number of approved loans this system can process in 5 hours? Now, what is different about this example is that we have step 3 and step 4 happen in parallel. Okay, so it's going to be interesting. How do we analyze a process where 2 steps happen in parallel? Because before we're looking at sequential processes only. And when you have these 2 steps in parallel, step 5 needs both of those steps to be completed before step 5 can complete the paperwork for the new loan. If step 4, let's say, gets done earlier, step 5 cannot be done until the credit rating comes through step 3. So both step 3 and step 4 have to be done for a loan application for it to advance to step 5. Okay, so let's look through and try to identify the bottleneck. We know bottleneck has the lowest capacity. And because capacity is the inverse of cycle time, capacity equals 1 over cycle time, the lowest capacity means the highest cycle time, right? Because the more the cycle time, the slower that part of the process is. It takes so long on one unit. So let's look for the highest cycle time. So when we examine that, we see that step 2 has the highest cycle time. So step 2 must have the lowest capacity. And you can verify that. Capacity of step 1 is 1 over 15 units per minute. But usually when I talk about capacity in units per hour, so we can multiply that by 60 minutes per hour. So 60 divided by 15, or 4 units per hour is the capacity of step 1. Step 3 capacity will be 60 over 20, or 3 units per hour. Step 3 would be 4. Step 4 would be 5. Step 5 would be 6 units per hour. So we see step 2 does have the lowest capacity of 3 units per hour. So step 2 is the bottleneck, and then the capacity of the entire process is the capacity of the bottleneck. So that will be 3 loan applications per hour. That'll be the answer to question 1. Okay, so that's question 1 answered. Really straightforward. Identify the bottleneck. And the bottleneck could be one of the parallel steps. Let's say step 2 took 10 minutes instead of 20, right? So then it's no longer the bottleneck. Then the bottleneck would be step 3 and step 1. They're both equally bottlenecks because they're both the slowest steps. And then your capacity of the bottleneck step 3 is 4 units per hour. 4 loan applications per hour. Step 1 is also 4 loan applications per hour, right? So your process capacity will just be 4 instead of 3 if step 2 cycle time was 10 minutes. So, something that happens in parallel can very well be the bottleneck. What is the throughput time? So this is very interesting. And again, we are not given waiting time, so we're not going to add the waiting time. Although in reality, in real life, throughput time is going to be, we add up all the cycle times and then we add the waiting time as well. Okay. So step 1 takes 15 minutes. So let's just walk through a loan application. Loan application enters the system at step 1. It takes 15 minutes. Then it takes 20 minutes. That's 35 minutes now. Then it's going to be worked in parallel for 15 minutes and 12 minutes. So step 4 gets done after 12 minutes, but we'll take the step 3 time because both steps have to be completed before we can move to step 5. So when you have something in parallel like this, you'll take the maximum of the times of the activities in parallel and use that to be added to your throughput time. And you'll not add both 15 and 12. So don't do, 15 for step 1, 20 for step 2, 15 for step 3, plus 15, and then plus 12 for step 4. You can't add both step 3 and step 4 because they happen in parallel. You only add the maximum of the two. So you do 15 plus 20 plus maximum of 15 and 12, which is 15, plus 10. Okay. So let me show you right here. Throughput time to complete an approved loan application is 15, step 1, plus 20, step 2, plus maximum of 15 and 12. So the maximum of step 3 and 4, because they run in parallel, plus 10. So 15 plus 20, 35, plus 15, 50, plus 10, 60. This equals 60 minutes, plus any waiting time in the system, which we are not given. So we'll just enter 60 minutes into our test or homework if this was a question there. Okay. So last question, what is the maximum number of approved loan applications the system can process in 5 hours? Okay, so we already know the capacity of the process is 3 units per hour from step 1, the question 1. And so in 5 hours, just multiply that by 5. So the capacity of the process in units per hour times the time you give it, 5 hours, should be the answer to question 3. So that will be 5 times 3 or 15. The bank will be able to complete a maximum of only 3 loan accounts per hour. So 15 loan accounts in a 5-hour day, because that's 3 times 5 is 15. Okay, now we're going to consider another example where we're going to add a little bit more complexity to model more real-life processes. Okay, so let's look at some more examples. Okay. So in this example, we added an additional worker to our bottleneck step, step 2. So remember, previously, step 2 was the bottleneck with just one worker, and our process capacity was 3 loan applications per hour. Okay, so each step is handled by one person except step 2. Step 2, we have 2 workers. Okay. Also, step 1 was modified. It used to take 15 minutes, but now it's taking 10 minutes. So these are the 2 changes. Okay. So what is the bottleneck? What is the capacity of the entire process? Now that we have 2 workers in step 2, we're not going to use the old 20 minutes as the cycle time, because the cycle time of one worker. Every 20 minutes, the 2 workers complete 2 applications, not 1. So the cycle time is going to be 10 minutes. You divide 20 by the number of workers. 20 is the cycle time for one worker. Because the workers work in parallel and every 20 minutes they complete 2 applications, you divide 20 by 2 to get 10 minutes per application, because cycle time is always the time needed to process 1 unit. If you are processing 2 units in 20 minutes, then 20 minutes is not the cycle time. Cycle time is the time taken to do 1 unit. Okay, and so the cycle time will be 10 minutes here for step 2. So now if we try to find the slowest step, the one with the longest cycle time, which will be the bottleneck, because longest cycle time means lowest capacity. Step 1 is 10 minutes, step 2 is 10 minutes, step 3 is 15, and that is the highest, right? Because step 4 is 12, step 5 is 10. So step 3 will be the bottleneck. And then the capacity of the whole process will be determined by the capacity of step 3. So what is the capacity of step 3? Capacity is always 1 over cycle time. So it's going to be 1 over 15 units per minute. But we don't like to think of capacity in units per minute. So let's just multiply that by 60 to get units per hour. So we're going to have 60 times 1 over 15, or 60 divided by 15, which will give us 4 units per hour, or 4 loan applications per hour. So that is the new capacity. So remember, before capacity was 3 loan applications per hour. When we added a worker to step 2 to have 2 workers working on step 2, now step 3 became the bottleneck, and our capacity went up from 3 loan applications per hour to now 4 loan applications per hour, and our bottleneck has moved to step 3. What is the maximum number of approved loans this system can process in a 40-hour work week in steady state? Very easy peasy lemon squeezy. You take your bottleneck capacity, which is the capacity of the process, right, which is given to you in units per hour now, 4 units per hour, and you multiply it by 40 hours, how much time you have. So in 40 times 4, you can do 160 loan applications in a week. If the target is set to process 150 loan applications each week, what is the utilization rate of each step? So this is the question where we have the demand or the load on the system, which is less than the bottleneck capacity, or less than the process capacity, which is, so because the process capacity / bottleneck capacity is 160 per week, and the demand or the load on the system is 150, we can calculate the utilization for each step using the 150 number. Remember, if 150 loan applications was not given, we just said, okay, calculate the utilization of the system, then we'll just assume the bottleneck is the limiting factor, and we would look at, the cycle times versus the cycle time of the bottleneck step and calculate the utilization like it was shown to you in a previous example. Okay, and I also showed you the example of what to do when you're given a load on the system or the demand on the system and how to calculate utilization. So we covered that in the utilization section before. We're going to do this again now. So let's look at how we do that. Okay, if the demand, the load on the system is 150 loan applications per week, the utilization or step 1 utilization would be 150 divided by the capacity of step 1, because 150 is how much step 1 would actually handle, right? Because that's the load on the system. It's not going to get more than 150 applications in the week, and it can actually do 160 because it can actually do how much? Its capacity of step 1 is 6 applications per hour, 60 over 10, and then for 40-hour work week it can do 6 times 40 or 240. So it's only going to do 150. It can do up to 240, so the utilization will be 150 over 240. So we do 150 divided by 240, and then you always, to convert to a percentage, you can multiply by 100, because when you do 150 over 240, the calculator will show you 0.625, right? And so you can just multiply that by 100 to convert to a percentage. And on a homework exam, the question will tell you enter the answer on a percentage scale like 0 to 100%. And usually you are asked not to type in the percent sign, so you just type in 62.5. And so that's the utilization. So the actual load on the system divided by the capacity of that individual step. Now, because the load on the system is given per week, we have to convert the capacity into per week. So we converted 6 units per hour times 40 hours to get capacity per week. Step 2, remember our cycle time is going to be 10 minutes because we have 2 workers, not 20 minutes. Okay, so with 10 minutes, the capacity of step 2 is the same as capacity of step 1. It's going to be 6 loan applications per hour, 60 over 10 minutes, right? And so again, we do 150 divided by 6, the capacity per hour, times 40 hours. This gives us the capacity per week. So 150 over 240, that gives us 62.5%. Now let's look at step 3. Step 3 has to handle 150 loan applications too, because remember, when a process diverges like this, okay, and there's no rhombus for a decision point, that means these steps in parallel will happen for every unit. If there was a decision point, let's see if I can draw that to show you. Okay, let's so if you had something like this, a step, then you had a decision point, and then you had something like this, okay? And let's say, whatever comes here, you check is it type A or type B, and then type A goes here and type B goes here. Maybe there are 2 types of loan application, the 2 types of products. Then these steps on this upper path will only happen for some of the units, and only the bottom task will happen for the other units. Right? So that means you are routing the units. Some units go on the upper path, some go on the bottom path. Okay? So that's a different situation than what we have. What we have is step 2. Okay? And then every loan application goes through these 2 parallel steps. How do I know every application has to go through these 2 parallel steps? Because there's no decision point here, which is selecting some applications to go for the top, some to go for the bottom. Okay, so this and this have to happen for every single application. So if the load on the system is 150 applications per week, the load here is also going to be 150, and the load here is also going to be 150. Okay, so that is why when we look at the utilization calculations, you're going to find the capacity of step 3, which is going to be 4 units per hour times 40 to come to the weekly capacity. And then the load is going to be 150. So you take 150 for step 3 divided by 4, the capacity per hour times 40 hours. That's the capacity per week, 160. So 150 over 160 gives you 93.75% utilization. And then you just repeat the process. Step 4 is 12 minutes. So that's 60 over 12 is 5 units per hour. That's the capacity of step 4. So you multiply the 5 by 40 hours per week to convert the capacity into units per week. 150 over 5 times 40, which is 200, gives you 75% utilization. Step 5, again, the load on step 5 is 150. right? Because when both step 3 and 4 are done, step 5 has to work on that application. It's not that step 3 gives a copy of the application, step 4 gives another copy, and now step 4 has to do two applications per application that came in. No, it's just the same application. So if there was load was 150 on step 3 and load was 150 on step 4, then step 5, the load on step 5 is also 150 applications per week. So again, step 5 utilization is 150 divided by the capacity of step 5, 60 over 10 is 6 units per hour times 40 hours in the week. So that's 240 capacity per week. So 150 over 240 gives us 62.5% utilization. So I hope that is clear. If it is not clear, read the slides carefully, think in your head how things are working, and rewind and rewatch this part of the video, and hopefully you'll be able to agree with me that this calculation is correct and makes sense to you. Okay, now a very interesting twist in the story in question 4. If step 3 is only needed for 20% of the applications, what is the new utilization of step 3? And what is the new overall process capacity? Okay, so now, let me go back to my diagram. Okay, so before, the load was 150 here and 150 here, but now the load here is going to reduce, because not every application needs a credit check. This is step 3, which is a credit check, right? So let's redraw. Okay, so we have step 1, S1. Then we have step 2, S2. Okay, then we have this S3, which is a credit check, S4. And then we have step 5. Okay, and we know that the load on the system is 150. That will be the load here. That'll be the load here. That'll be the load here, because step 4 happens for every single application. That'll be the load here. S5 happens for every single application. But the load here is going to be 20% of 150, because the question tells us we only need to do a credit check for 20%, maybe of the high risk applications or whatever. So we do 0.2, 20% times 150. That will be the load on this step. Okay, and so we can calculate the utilization. The utilization U1 of station 1 will be 150 over capacity of station 1, which was 6 per hour times 40 hours per week, right? And so it'll be the same. Nothing will change. Like, it'll be the same as last time, 62.5%. Everything will be the same. The only thing that will change will be the utilization of S3. So the utilization of S3, let's call it U3, okay, U3, would be equal to 0.2 times 150. That's the new load on S3. Okay, divided by the capacity of step 3 in terms of applications per week. The cycle time of step 3 was 15 minutes. So 60 over 15 gives me 4 units per hour times 40 hours per week. So that is the capacity per week of step 3. So 0.2 times 150 divided by 160 would be my utilization of step 3. And that's the only thing that will change. Okay, so let's go back here and see. So for here at the bottom of the slide, if only 20% of the customers need step 3, where is my, wait, yeah, utilization of step 3 would be load on step 3, which is 0.2 times 150, like we discussed at the bottom of the slide, divided by 160, just like we discussed, and that's 18.75% utilization. Okay. Okay, now let's talk about the capacity when that happens in question 4. Okay, so we talked about utilization first, on how the load is different on step 3, and the utilization is this number right here. Okay, what about the capacity of the system? And let me just erase the utilization stuff and talk about capacity, because now it's a little bit complicated, because 20% of the applications need to do step 3, but 80% don't need to do step 3. Okay, so I'm going to write the cycle times here so we can see the bottlenecks. and talk about it, okay? Okay, so the cycle time of step 1 is 10 minutes in this new version of the problem. Cycle time of step 2 is 10 minutes. Remember, it used to be 20, and then we added two workers, and so it became 20 over 2 equals 10 minutes. So that's where this 10 minutes comes from. That was given in, the two workers was given in the question, okay? Then the cycle time for step 3 is 15 minutes. Cycle time for step 4 is 12 minutes, okay? And the cycle time for step 5 is 10 minutes. And we know that this needs to happen for only 20% of the cases. Okay, so now we actually have two paths to the system. Let's think about an application for which step 3 needs to happen like the old way. It goes through here, it goes through here, it goes through here, it goes to both of these paths. So this happens, then it goes through step 5, and it goes out the system. So it's just like the old times, like the initial problem. And for these orange applications, okay, the bottleneck is going to be this, which is the highest cycle time. And so the capacity for the orange applications, which need the credit check, that's going to be 60 minutes over 15, and that's going to be 4 applications per hour, or 4 units per hour, okay? But we also have, let me get my color coding correct. Let me erase that green one. So I'm going to use the green color. We also have these green applications, which go through the system faster. So they go through step 1, they go through step 2, but then they only go through step S4. They skip the credit check, they go through S5, and they go out. So for the bottleneck for these green applications cannot be S3, because S3 never happens for these green applications, and they're 80% of the applications. So to find the bottleneck for the green applications, we have to figure out what is the bottleneck if step 3 is not there. So if step 3 is not there, then S4 becomes the bottleneck, and so the capacity for the green applications is going to be 60 minutes over 12, which is going to be 5 applications per hour, or 5 units per hour. And so now we have a tricky situation, okay? If we only get applications like the orange applications, we'll be working at 4 units per hour, or 4 applications per hour speed. That's the capacity of the whole process. And if we only get the green applications, we'll be working at 5 units per hour, okay, or 5 applications per hour. That's our speed. But what if we get a mix? What if we get a mix of applications? Well, then our effective capacity on average will be a weighted average of these two numbers. And we know that this is 20%. 20% of the applications need a credit check. 80% don't. That's given in the question. And so our actual capacity, like our average capacity, and this will not be an average capacity, okay? Because if in 1 hour we only got orange, then it will be 4, and the next hour we only got green application, it will be 5. But usually we're going to get a mix of them, 20-80 mix, 20%, 80%. And so the average capacity will be 20% times the orange capacity of 4 plus 80%, this is 0, 80% times the green capacity of 5, and then we just calculate that, okay? And because I already did it on the slides, let's see what it comes out to. So when we calculate that, 0.2 times 4 plus 0.8 times 5, you get 4.8 loans per hour, okay? So that's 4.8 loans per hour, or units per hour, because loan is our unit, right? So that's the weighted average. You multiply by the percentages of the two, okay? If you had 50% orange, 50% green, you can take a simple average. You can just do 4 plus 5. That's the capacity of orange. Capacity of green is 5. Divided by 2, you get answer is 4.5. 4.5, the simple average only works if they're even split, 50-50. But if the split is not even, you have to do this weighted average, 20% and 80% like that. Okay. So here in the middle of the slide, I'm saying, what if it was half-half? You'll get 4.5, but it's not half-half. So you'll do a weighted average, you get 4.8 logons per hour. So that'll be the answer. Okay, last example. And in this example, I want to show you what to do when you have multiple people doing a step. We already saw that here, right? We had 2 workers doing step 2. But what's even more interesting here is that we have 3 workers, A, B, C, doing step 3, T3, but each worker works at a different speed. And so the cycle times are different. When we put 2 workers here in step 2, both of them were equally proficient. And so both of them were done in 20 minutes. So every 20 minutes, we got 2 units out. So the average cycle time became 10 minutes per unit. But here, the workers don't work at the same speed. So after 10 minutes, we get a unit out from B, but A is still working and C is still working. So it's more complicated. Your workers working at different speeds. And this can often happen. So here, we have a dress. These are people who work on dresses, alter dresses. So they are like people who know how to stitch and sew and so forth. And so they work at different ways. Maybe the guy at B, T3B, that's very experienced and super fast. And maybe T3A is a new worker, just barely trained. And so that new worker is slower, right? So you have this kind of situation, which is why it's not that step T3A, T3B, T3C are happening in parallel. It's just the same step, but the workers or the machines you have, they work at different speeds, okay? Now, sometimes we draw a situation like that. So we had, T2 followed by T3, and T3 has 3 workers. So what sometimes we'll do, let's put a sign of a worker and put the cycle time here. That was 14 minutes for worker 1. Then worker 2 is 10 minutes. And then worker 3 is 11 minutes. So all these 3 workers are doing T3, but they all have different cycle times. You can show it like this. If you want to be really explicit, because yours, I'm doing this type of problem with you for the first time. So I want to really show the different speeds of the workers working in T3. So I drew it like this, okay? But because this kind of can give the sense that these are, 3 different parallel steps, like in that loan application, you have 2 different steps happening in parallel. It can confuse the reader or the viewer to think, oh, these are 3 different things happening. This is only for teaching purposes. In real life, I would do something like this. I can just make one box and make 3 worker signs and give their different cycle times and kind of make a note, maybe, okay, 3 workers at different speeds. So each worker works at a different speed. So maybe I'll put a note like that, maybe give each worker cycle time to indicate that, so that the reader is not confused that this is 3 different things happening in parallel, okay? But hopefully you understand what we're trying to do here, okay? Okay, so let's look at this process. We have step T1 that is taken care of for all customers. Then we have a decision box because we have 2 types of customers. The decision box will say, okay, what type of customer is this? If it's type A, it will go to step T2 at the top in the blue color. Then it'll go to step T3, whichever of the workers is available. Notice there is only one step T3. A, B, and C refer to different workers that can do step T3. So each unit will only go through one of them. So either it'll go to T3A, T3B, or T3C. Okay. So for every unit, only one of T3A, B, or C will happen. Then it'll go to T4, then T7, and that's the end of the process. If it's a type B customer, then after T1, type B customer will be routed towards the bottom path, which is in this light purple color. And so it'll go to T5, and then T6, then T7, and then be done with the system. In the number in the parentheses are the cycle times in minutes. So T1 takes 12 minutes to do 1 unit or 1 customer. A unit is a customer in this case. T2 takes 30 minutes and so on. So let's look at the questions that we have. What is the capacity per hour for type A customers? Assume no customers are waiting. So when we want to calculate the capacity for type A customers, we're going to assume only type A customers are coming in the system. So step T1, the full capacity is available to type A customers. Step T7, which is shared between both types of customers, the full capacity is available to type A customers. And then we can also calculate the capacity for type B customers. Okay, so for type A customers, we need to find the bottleneck. Now, usually we found the bottleneck by comparing the cycle times, and we said the longest cycle time is the slowest process step, and so that is the bottleneck, right? And if you look at 12, 13, 14 is the longest cycle time, T3A, okay? But is step T3, because T3A is just step T3, so is step T3 the bottleneck or not? And the answer is no. Why? Why is step 3 not the bottleneck when T3A has the highest cycle time? Because we compare cycle times because they tell us about capacity. Capacity is 1 over cycle time. However, for T3, the capacity is not 1 over 14 because T3B adds additional capacity to step T3 and T3C provides an additional source of capacity to step T3. So the capacity of step T3 is the capacity of T3A plus T3B plus T3C. So the capacity of step T3 is actually quite a lot. Okay, so to actually find the bottleneck, we have to compare capacities, because when you have these 3 workers working in parallel and they all take different amounts of time, you don't know the cycle time of step T3. Okay, so let me explain that on the diagram I can draw here. So I'm going to show you 2 situations. Okay, this was the situation where you had 2 workers. Okay, and this step took 20 minutes with 1 worker, and the cycle time here was let's say 15 minutes. Okay, and so we said, well, the effective cycle time here, the effective cycle time is just going to be 20 minutes over 2 workers, or 10 minutes. Okay, 10 minutes. And now we can compare the cycle times and say this is the bottleneck. Okay, but now we have a situation where the 2 workers take different times. So worker 1 takes 20 minutes and worker 2, let's say, takes 14 minutes. And now we can't say, oh, 20 over 2 or 10 minutes is the cycle time, because every 20 minutes, more than 2 things come out. So the effective cycle time is not just 20 over 2. Okay, because 2 point something units will come out every 20 minutes, because when it's done 20 minutes, it's done 1 unit, and this is done like 1.5 units or something. So 2.5 units approximately come out every 20 minutes. So you can't just do 20 over 2 to get the cycle time of 10 minutes and compare 10 to 15. So what you do in this type of situation is you compare the capacity. So capacity here is 60 over 15, which is 4 units per hour. Okay, and the capacity here is going to be 60 over 20 for this worker plus the capacity for this worker, because they both are in the step, they can work in parallel. That's going to be 60 over 14. Let's make it 15 so it's easier to calculate for me. 60 over 15. Okay, and so this capacity, this is going to be 3, it's going to be 4, so it's going to become 3 plus 4, or this is going to equal 7 units per hour. When workers work in parallel on the same step, you just add up the capacity. So remember this rule. When multiple workers work in parallel on the same step, you just add up the capacity of each worker. Once you add up the capacities of all the workers, that is the capacity of that step. You can add up capacities. Do not add up cycle times of workers working in parallel. Okay, so when you add up the capacity is 7 units per hour. Here is 4 units per hour. So this is the bottleneck because the lowest capacity one has to be the bottleneck. So that's the logic we're going to follow here. Okay, so if you add up the capacities, you'll see that this capacity is very high, and the bottleneck, I believe, is going to be step T2. Okay. So here we're adding up the capacities for step T3, 60 over 14, that's capacity of T3A, plus 60 over 10, capacity of T3B, plus 60 over 11, capacity of T3C, or 15.74 customers per hour. So that's a very high capacity of step T3. So then when we compare step T4, that's a capacity of 6, 60 over 10 is 6 customers per hour. T1 is 5 customers per hour, and T2 is less than 5 because 60 over 13 is 4.62. So step T2 is the bottleneck for type A customers. It has the lowest capacity at 4.62. T1 has a capacity of 5, T4 has a capacity of 6, T3 has a capacity of 15.74, and so clearly step T2 is the bottleneck for type A customers. Okay, let's go back. If 30% of the customers are type A, 70% are type B, what is the average capacity? So first, we have to find the capacity of type B workers. That's easier because there's nothing complex happening on that path. You go T1, T5, T6, T7, that path. So here we see T6 has the highest time, so the highest cycle time. So the bottleneck is T6. So the capacity for type B workers is going to be 60 divided by 22, which is slightly less than 3. And so that will be the capacity here. And then we're going to take a weighted average. So 30% times capacity for type A plus 70% times capacity for type B. So let's do that. So capacity for type B workers, as I just told you, because step T6 is the bottleneck, is going to be 60 over 22 or 2.73. Then the average capacity of the process becomes a weighted average. 30% are type A customers, so 0.3 times 4.672, which is the capacity of for type A workers, type A customers, plus 0.7 times 2.73, where 2.73 is the capacity for type B customers. This weighted average gives us 3.29 customers per hour. Okay, that's the average capacity of the process, based on a 30-70 split between type A and type B customers. Obviously, if this customer mix changes, we'll have to calculate the average capacity again. Assuming the arrival rate is more than 5 customers per hour, where would you experience waiting times for type B and type B customers? Okay, and when you look for type A customer waiting time, you can assume that there's only type A customers coming at that time, no type B, and for type B, you can look at only type B. Okay. So, arrival rate is more than 5 customers per hour. Now, if you look at T1, okay, what's coming into T1 is more than 5 customers per hour. Okay, what can T1 handle just by itself? T1, what is the capacity of T1? Capacity of T1 is 60 over 12, which is 5 customers per hour. Okay, so the load on T1 is more than what it can handle. It can handle 5 customers per hour, but the load on T1 is what's coming in. Okay, the load on T1 is what's coming in, which is more than 5. More than 5 is coming into T1. T1 can only put out 5 customers per hour, can only handle 5. So the queue will start to form right here. Okay, so we will get a queue forming right here. Okay, now after T1, you only get 5 customers per hour being sent out here, because even though more than 5 arrive per hour, T1 can only handle 5. So after that's 5, right? So let's look at type A customers. How much can T2 handle? The capacity of T2 is 60 over 13, okay, which would be a little bit less than 5. Okay, so you can do that. It's gonna be 4.9, something like that, right? So T2 can handle 4.9 customers per hour. The load on T2, if only type A customers are coming in, okay, all of these 5 customers, all of these 5 are type A, then the load on T2 is 5, but it can only handle 4.9, so a queue will form here as well before T2. Because whenever the load on a process step or the demand for that step is more than what it can handle, a queue will start to form outside it. Okay. Now after T2, sorry about that. So the output here of T2 will be 4.9 customers per hour going into step T3. T3, remember the capacity of T3 was 15 point something, it was more than 15. So there's going to be no queue formed here because whatever comes out of T2, T3 can just gobble it up. It can handle it, right? Because the capacity is much more than the load on T3. So that's fine. So because the capacity of T3 is more than 4.9, the output here is also going to be 4.9. 4.9 goes in, just passes right through T3. T3 does not slow down the 4.9 output of T2. So the load on T4 is 4.9, but T4 can handle up to 6 customers per hour because the cycle time is only 10. So 60 over 10 is 6. So because T4 can easily handle the 4.9, we won't really get a queue forming here. Okay, so this will be no problem here. And then, so 4.9 will go into T4 per hour, 4.9 will come out per hour. And then T7 can also handle 6. So 4.9, a load of 4.9 is no problem. So nowhere else will queues form. This the queues that we are identifying here are queues that will last, that will grow temporarily for short units of time. If the arrival rate is random, so you get sometimes 6 customers per hour, sometimes 7, sometimes 3, sometimes 10, right? If the arrival rate is random, then these are just average numbers. So sometimes, more than 4.9 might come out of T3. No, actually, no, wait. T2 can only give out 4.9, so only 4.9 will come here. Here, before T1, sometimes less than 5 might arrive if the arrival rate is random, it's going up and down. And so the queue here can go up and down depending on the arrival rate, but on average, there will be a queue here because the average arrival rate is more than 5. Okay, but after you go from T1, the processing time is always 12 minutes. That's not random. So you only get 5 customers per hour going out of T1. If this processing time was also random, if sometimes T1 could handle 5 customers per hour, but sometimes it could handle 3, sometimes it could handle 7, then this would be 5 on average. And then you may get, this is a 4.9 on average, this could go up and down. And then you may get, sometimes a small queue forming in other places as well as the load changes. And if the load here, for example, goes to 6 or above, you may get a small queue form here, then it'll fall back down to 4.9, and then the queue would go away. So these are, if these are averages, then you could get behavior which deviates from the average at some times. But if the processing times are fixed, these are not variable, then you'll only get a queue before T1 and T2. Otherwise, you'll only get sustained queues before T1 and T2. The other queues will be very ephemeral if they ever come because of random service times. Because if this time is random, it is an average time. It can take more or less than 12 minutes, more or less than 13 minutes. Then any other queues will be ephemeral. Okay, but T1 and T2. So a queue forms whenever the load on that process step is more than the capacity of the process step. The load on the first process step is given by the demand. The load on the other process step is given by the output of the previous step. Let's do it for type B customers. Okay. Again, the queue will form before T1 because the load arrival rate is more than 5. T1 can only handle 5, so the load is more than the capacity of T1. Okay, what about here? So this can handle 4 customers per hour based on the cycle time of 15. What's coming out here is 5 customers per hour. 5 is more than 4, so you'll get a queue here too, type B. And type B gets a queue here too. Okay, then T5 will spit out 4 customers per hour. T6 can handle only 3 point something, 3.7 or something, like 60 over 22, which is less than 4 for sure, right? And so a queue will form here too, because the load on T6 is 4 customers per hour, and it can handle less than 4 customers per hour based on its capacity. So you get a third queue here. Then this will, T6 would spit out 3 point something customers per hour. T7 can handle up to 6, so this step is fine. The load is less than the capacity for T7. So for type B customers, queues will form before steps T1, before steps T5, and before steps T6. We just compare the load on that process step with the capacity. Okay, so that is it. If you have any questions, you don't understand any example, please feel free to reach out to me. And you can obviously watch the video again. Hopefully, you'll get the hang of it, the main ideas, and then you can try to solve, problems like this on your own to make sure you understand these calculations.